In this lesson, we're going to introduce the superposition rule for differentiation. The superposition rule investigates how adding functions and multiplying them by constants affects their derivatives. So this rule is actually pretty general. So to get to it, I'm going to start by multiplying two functions f of x and g of x by some constants a and b. And then I'm going to add the result, so we get this. Now, when I see something like this, I get a little bit worried because it doesn't really tell me very much. So instead of this formula, how about I draw a picture to show you what I'm talking about? So this formula over here represents the exact same information as this picture over here. On the left-hand side, we have h of x, and that's represented by this big machine over here. As you can see, feeding x through h of x is the same thing as first feeding it through f and g, and then multiplying f of x by a, before proceeding to multiply g of x by b. After this, we add both of these to produce the same thing that we would get from h of x. So in this lesson, we'd like to find the derivative of h of x, and we'd like to see how it's affected by f of x and g of x. Now, to actually find this derivative, dh of x on dx, we have to investigate how changes to the input will affect the change in the output. Or to say this in another way, we want to see how changing the value on the left over here will affect the value on the right. To begin with, I just want to remind you of the definition of dh on dx. So to put this simply, we're going to change x by a little bit, and then we're going to investigate how this affects the value of h. As we make the change in x as small as we possibly can, eventually, in the limit, we can find the value of dh on dx. Now, so far, we've been a little bit abstract. So how about I choose some specific functions, and I'll show you how their outputs change as we change their inputs. So here we've got a pretty simple problem here. We've set change in x to be equal to 1, and I've given you some random function h of x. At the point where x equals 2, how much does h of x change when we change x by 1? Now, to work this out, I'm going to draw h of x, but I'm also going to draw the middle values as number lines to help us out. So let's start by looking at this term, 2x cubed. We start with x, we cube it, and then we multiply it by 2. And then for this term, minus 5x squared, we start with x, we square it, and then we multiply it by minus 5. Remember, you have to imagine that there's an imaginary plus sign between these. So after this, we just add these two terms together, as you see here, to get h of x, as we have here. Now, we said we wanted to track x equals 2. So let's start by marking x equals 2 on the first number line. Now, first let's go up the top branch. So if we take 2 and then cube it, we're going to get the number 8. So let's mark that as well. And now that we have 8, we can also multiply by 2 to get 16 on this graph. Now, we can't actually do the addition because we don't know what the value here is. So now we have to go down the bottom branch as well. So for starters, we can take 2 again and we can square it first to get 4. Now after this, we can go ahead and multiply 4 by minus 5 to get the value of minus 20. And now that we have both of these values ready, we can go ahead and add them, and this will give us minus 4, because minus 20 plus 16 is minus 4. Now that we know what happens when x equals 2, we said that we wanted to see what would happen to the output when we change the input by 1. Now, because change in x is equal to 1, we've just moved from 2 up to 3. Now, just like we track the number 2 through the whole machine, we'd also like to see how 3 tracks through the whole machine as well. So let's start by actually cubing 3. If we cube 3, we get 27. And now, 27 times 2 is just 54. Now we go back to the beginning, and then we square 3. And if we square 3, we get 9. And now, 9 times minus 5 is just the same thing as minus 45, which we can write down here. And now, we're ready to add the green circles as well. 54 minus 45 is just the same thing as 9, which we can mark here. Now, I want you to remember that we changed the input by 1. And when we did this, the output has gone up by 4 plus 9, which is the same thing as a change in 13. So initially, I just look at this and I say, okay, I changed the input by 1 and the output seems to have changed by 13. That's great. So what? However, if you actually go back by one level and look at the changes in these values over here, you'll notice that something a little bit deeper is happening. To go from 16 to 54, you have to increase by 38. And to go from minus 20 to minus 45, you actually have to decrease by minus 25. And now you notice something cool. 38 minus 25 is the exact same thing as 13. So it looks like as well as adding the values, we're also actually adding the change in the values as well. And that's actually a really cool property of addition. Now seeing why this is true is actually pretty easy. We're just adding 54 minus 16 and minus 45 minus minus 20, or plus 20. Or more generally, if I just label this G1 and this G2, then I label this R1 and this R2, then this 9 over here is just going to be G1 plus G2. And from this we're just subtracting minus 4, which is the same thing as R1 plus R2. This is the same thing as change in H. Now if we just expand these brackets over here, we can rewrite this as G1 minus R1 plus G2 minus R2. And now if we look carefully, we notice that G1 minus R1 is the same as the change in the top value here. And then G2 minus R2 is just the change in the bottom value over here. So therefore we conclude that change in H is just the same thing as the change in the top plus the change in the bottom. So we can just add the changes as well as the values. Now this here is actually really useful, but we can take it even further. Let's go back one more layer to see what happens there. Now looking at this top value over here, we notice that 27 minus 8 is just 19. And if you actually think about it for a moment, you notice that 19 is just the same thing as the change in the function f when we fed both of these points through it. Now since you're actually doubling both of these values to get from here to here, you must also be doubling the gap as well, and we see that. 19 times 2 is just 38. Now because 19 times 2 is just 38, then we can say change in f times 2 is just equal to this gap over here. And now we can do the exact same thing for this gap down here. We can see that this is just 9 minus 4, which is the same thing as 5. Now since this bottom function here is also the same thing as g of x, then 9 minus 4 is the exact same thing as the change in g of x. And again, the gap here was 5, and once you've gone ahead and multiplied it by minus 5, the gap became minus 25, so the gap has also multiplied by minus 5. Now as we explained before, the gap from here to here is exactly the same as the sum of these two gaps over here. And therefore we can actually say something interesting. Change in h is just going to be the exact same thing as 2 times change in f minus 5 times change in g. Now I want you to notice how similar that is to the original function. H is just the same thing as 2 times f minus 5 times g. Now from this example, I want you to have two main takeaways. We can multiply gaps by constants to increase their size. And it's also possible to add gaps together to make new gaps as well. So now we just want to apply this to the general case too. Now just like we did in the example, I want you to imagine that we nudge the value of x by a small amount that we call change in x. Now again, like the example, when you feed change in x through f, you're going to get a change in f. And if you feed through g, you'll just get a change in g. Now as we saw, multiplying change in f by some constant a will just make the gap grow by the value a. So you're going to get a times change in f over here. And again, by multiplying change in g by b, we also get b times change in g over here. Now finally, if you go ahead and add a times change in f and b times change in g, you'll get the final value over here, which is h of x. And now this actually leads us to something pretty interesting. We notice that a times change in f plus b times change in g is the exact same thing as h of x. So h of x equals a times change in f plus b times change in g. And now we can also go ahead and replace change in h for these two values over here. Now that we have this over here, we can go ahead and break this fraction up into two parts. And now after this, we can just pull this a out in front of the fraction, and we can also do the same for b. Now if we want to continue any further, we have to use the limit laws. If you actually haven't heard of the limit laws before, that's totally fine, because we're going to use two really simple ones. Now I'm not actually going to prove them in this video, but I will do so in another video. Now loosely speaking, anytime you see a limit attached to a bracket like this, you can basically treat it like a normal bracket, with a few exceptions, but we're not going to need them for this particular case. And therefore we can actually start by breaking this limit up into two different terms. And now, just like we would for a normal bracket, we can also rip these constants right out of the brackets as well. Now if we look carefully at this term over here, it's actually the same thing as df on dx. And similarly, this term over here is just the derivative of g with respect to x, or dg on dx. And now we've actually reached a really important formula here. We notice that if we have two functions multiplied by constants and then added, then the derivative of those functions is given by just taking the derivative of each individual term separately and pulling the constants out in front. Now I'd like to show you why this is useful. So to do that, I'm going to go ahead and find a derivative of a particular function in this form. Now I've only proven this formula for the case of two terms, but there's nothing really stopping us from adding as many terms as we like. This formula is going to hold no matter how many terms you have. So here I've given you a case with 3 terms, so it should still work just the same. Now the first step to differentiate this is to break it up into a number of terms. Now because the number 4 doesn't change as we change the value of x, then we know that d on dx of 4 is just going to be 0. And now the other thing that the superposition rule tells us is that we can rip this 7 out of the derivative, so we should go ahead and do that too. Now in this form, I have no idea how to differentiate this thing, but by using the superposition rule, we've been able to convert this complicated derivative into 2 derivatives that we know how to find. These are just derivatives of multinomials. Now as we learnt before, we can just bring the power down on this value, so this 2 can just come out the front, and if we did it here, you just get 3x squared. And now finally, 7 times 3 is just 21, so we can replace that as well. Now from this we can just see that the derivative of x squared minus 7x cubed plus 4 is just 2x minus 21x squared. Now that's great and all, but I still feel like we're doing too much work for such a simple problem, so let me show you a bit of a shortcut. Now I have this silly little notation that I always use to help me find derivatives, so let me show it to you in the case of the superposition rule. Instead of actually writing out functions as letters, I just draw boxes or some kind of shape, as I'll show you here. It even feels silly saying this, but if you have some function represented by a square, and it's equal to a times another function represented by a circle, plus b times another function represented by this diamond looking shape, then we can actually write its derivative like this. Now in my head, I imagine checky boxes as derivatives. So therefore, if we have some function that's equal to a times some function plus b times a different function, then its derivative is equal to a times the derivative of the first function plus b times the derivative of the second function. You can see that this one over here is just the exact same as this, and this one over here is the exact same thing as this. So it's just the same thing written in a different notation. But the notation is actually pretty useful to actually help us solve actual examples. So let me go ahead and actually give you an example to show you why I do this. So to differentiate a function like this, I just start by drawing shapes around everything that I can already differentiate. Now I also draw a box around the function on the left because this is the actual function I'm trying to differentiate. Now as you can see, these shapes match this form over here, so therefore we can say its derivative is written like this. So I just copied over the 2 and the minus 21, and h of x just becomes h dash x because that's its derivative. Now the derivative of x is just 1, so I write that over here, and the derivative of x squared is just 2x, so I write that over here. Now 21 times 2 is just 42, so we can write this in its final form like this. And I hope you can see how easy that is. It's one of the things that calculus just always manages to do. Despite the fact that it's defined with limits, we almost never need to use limits when we're actually finding derivatives. And with this, we've actually completed our example. Now let's summarize the lesson. In this lesson, we looked at functions of this form over here, where we can add functions and multiply them by constants a and b. We found that if you make a small change to the input x, then the change to the output is given by a times f of x plus b times g of x, which is just like the form of the function that we started with. We also found that this is always true no matter how large change in x is. Then after this we remembered that the derivative of h with respect to x is defined with this limit over here. Using this fact that we found, and a little bit of algebra, we were able to show that this over here is always true. So the main takeaway of this lesson is, if you want to differentiate a function that involves multiple terms and constants, you can always just put the constants out in front and differentiate each term separately. And now with this, we've actually completed our discussion on the superposition rule for derivatives.